Brief Answers to the Big Questions by Stephen Hawking. Introduction. Imagine for a moment you receive an invitation to a party. The champagne is chilled, the canapés are ready, and the host is one of the most brilliant minds in human history. There's just one catch: the party already happened. Years ago. The host, you see, only sent out the invitations after the event was over. Why would he do such a thing? Because this wasn't just any party. It was a party for time travelers. And the host, the brilliant and ever-playful Stephen Hawking, sat there on the day of the party, surrounded by balloons, waiting to see if anyone from the future would show up. Did they? Well, we'll come back to that. But that simple, elegant experiment tells you everything you need to know about the man whose final thoughts we're going to explore today. He wasn't just a scientist locked in an ivory tower. He was a curious, imaginative soul who dared to ask the biggest, wildest questions imaginable. The book we're diving into, Brief Answers to the Big Questions, is special. It's not just another science book. It is Hawking's final message to humanity, a project he was working on in the last year of his life. It's his parting gift, a collection of his most profound, hopeful, and urgent thoughts, compiled by his family and colleagues after he was gone. For decades, Stephen Hawking was more than a physicist. He was a symbol of the limitless power of the human mind. A man who was told at 21 that he had only a few years to live, yet went on to travel the cosmos, not in a spaceship, but inside his own head. He unraveled the secrets of black holes, explored the very beginning of time, and became the most recognizable scientist since Albert Einstein. His book, A Brief History of Time, sold over 10 million copies, proving that millions of us, all around the world, are hungry for answers. And that's the promise of our journey today. By the end of this conversation, you won't just understand a few of Hawking's theories. You will have a new lens through which to see the universe, your own future, and the incredible potential that lies within the human spirit. We're going to tackle the 10 big questions that drove him his entire life, questions about God, about our survival, about our ultimate destiny among the stars. So, let's begin. Let's step into the mind of a true giant and see what answers he left for us. Book summary. To truly understand Stephen Hawking's answers, you first have to understand the man. And to understand the man, you have to go back to a boy who loved to take things apart. He grew up in a London house, playing in the rubble of a bomb site from World War II, his curiosity sparked not by pristine classrooms, but by the raw, chaotic results of an explosion. He wasn't a star student, his handwriting was messy, and his classmates nicknamed him Einstein, partly as a joke. One friend even bet another a bag of sweets that young Stephen would never amount to anything. That bet, it's safe to say, was lost. Because that boy was driven by a relentless need to know how things worked. This wasn't just about toys and radios. As a teenager, he and his friends would have long, passionate arguments about the biggest question of all: the origin of the universe. Did it need a God to get it started? Or could it have just happened? This question would become the engine of his life's work. But his journey to answer it was almost cut tragically short. In his final year at Oxford, he started getting clumsy. He'd fall for no reason. His speech began to slur. At first, a doctor flippantly told him to lay off the beer. But his mother knew something was seriously wrong. After weeks of tests, the diagnosis came. It was a brutal, unforgiving motor neuron disease called ALS. The doctors told him it would gradually destroy his ability to control his muscles, to speak, to eat, and eventually, to breathe. They gave him 2 years to live. He was 21 years old. He fell into a deep depression. What was the point of getting a PhD if he wouldn't live to finish it? What was the point of anything? He said his expectations were reduced to zero. And then, something remarkable happened. In that place of absolute zero, every new day became a bonus. He began to appreciate everything he did have. He fell in love with a young woman named Jane, who was determined they could fight the disease together. Her confidence gave him a reason to live. And if he was going to get married, he needed a job. If he was going to get a job, he needed to finish that PhD. And so, the work began. The same fire of curiosity that drove him as a boy was reignited, now sharpened by the profound awareness of borrowed time. As he put it, while there's life, there is hope. This personal crucible is the key to understanding all of his work. His exploration of the cosmos was never just an abstract, academic exercise. It was a testament to his sheer defiance, his refusal to be limited by his physical body. "I have spent my life traveling across the universe," he said, inside my mind. So let's join him on that journey. Let's start with the question that began it all, the one he debated with his friends as a boy. Is there a God? For thousands of years, this was a question for religion, not science. The world was a scary place. Lightning, storms, eclipses, these were the work of angry gods. The Vikings, as tough as they were, believed in supernatural beings to make sense of it all. Religion gave comfort, and it gave answers. But Hawking believed science now provides better, more consistent answers. He wasn't on a mission to disprove God out of spite. He simply wanted to find a rational framework to understand the universe. His work led him to a conclusion that he knew was controversial, but to him, was also inescapable. He says we can think of the universe as a kind of cosmic cookbook. To make a universe, you only need 3 ingredients: matter, energy, and space. Matter is the stuff, the dust, rock, gas, and stars all around us. Energy is what makes things happen. It's the heat from the sun, the force that drives the cosmos. And space is, well, lots and lots of space. For a long time, the question was, where did all this stuff come from? Who or what provided the ingredients? The first breakthrough came from Albert Einstein, who realized that matter and energy are 2 sides of the same coin. His famous equation, $E = mc², tells us that mass can be converted into energy, and energy into mass. So now, our cookbook only has 2 ingredients, energy and space. But the big question remained, where did all the energy and space come from? Science tells us they were invented in a single, explosive event we call the Big Bang. At that moment, an entire universe of space and energy came into existence. For many, this is where God comes back into the picture. The Big Bang was the moment of creation, and God was the creator. But Hawking pushes us to ask another question. What if you can get a whole universe for free? The secret, he explains, lies in one of the strangest facts about our cosmos, the existence of negative energy. This sounds like science fiction, but it's a real concept demanded by the laws of physics. Hawking offers a beautiful, simple analogy to help us understand it. Imagine a man wants to build a hill on a flat piece of land. To do this, he digs a big hole. The soil from the hole becomes the hill. He's created a hill, yes, but he's also created an equal and opposite hole. The hill is a positive, and the hole is a negative. Together, they add up to 0. The flat land is perfectly balanced. This, Hawking says, is the principle behind the universe. The Big Bang produced a massive amount of positive energy, the matter and energy that make up our universe, our hill, but it simultaneously produced the exact same amount of negative energy. And where is this negative energy? It's stored in space itself. Space isn't just an empty stage, it's the hole that perfectly balances the hill of creation. The positive and the negative add up to 0. What does this mean for the question of a creator? It means that if the universe adds up to nothing, you don't need a God to create it. The universe, in his famous words, is the ultimate free lunch. But wait. Even if the universe required no net energy, something must have triggered the process, right? Things don't just pop into existence out of nothing in our everyday lives. But our everyday lives aren't the whole story. If you travel down to the subatomic level, you enter the weird and wonderful world of quantum mechanics. In this realm, particles really can appear out of nowhere, stick around for a moment, and then vanish again. It's happening all the time, everywhere. Since we know the universe was once smaller than a proton, this means the universe itself could have simply popped into existence, just like a quantum particle, without violating any known laws of nature. This leads to the final, critical question. Did God create the quantum laws that allowed the Big Bang to occur? Is a divine being needed to set up the rules of the game? Here, Hawking takes us to the nature of time itself. We are used to the idea of cause and effect. Something causes something else to happen. So it's natural to think something must have caused the universe to begin. But this assumption breaks down at the moment of the Big Bang. To understand this, he asks us to think about a black hole. A black hole is an object so massive that its gravity is incredibly powerful. It warps not only space, but also time. As you get closer to a black hole, time itself begins to slow down. Inside the black hole, at the point of singularity, time doesn't exist. It stops. This, he says, is exactly what happened at the start of the universe. As we go back in time toward the Big Bang, the universe gets smaller and smaller, until the entire universe is a single, infinitesimally small and dense point, a singularity. And at that point, just like inside a black hole, the laws of nature tell us time itself must have begun. You cannot get to a time before the Big Bang, because no such thing existed. Time is a property of our universe, it didn't exist without it. This is the final key. If there was no time before the Big Bang, then there was no time for a creator to exist in. The question "what happened before the Big Bang?" is meaningless. It's like asking, what is south of the South Pole? It's a question that has no answer because it's based on a flawed premise. So, for Hawking, the simplest explanation is that there is no God. No one created the universe, and no one directs our fate. The universe was spontaneously created out of nothing, governed by the laws of science. He says we are each free to believe what we want, but this, for him, is the most compelling conclusion. And this leads him to a profound realization: there is probably no heaven and no afterlife either. He saw belief in an afterlife as wishful thinking. I think that when we die we return to dust, he said. But there's a sense in which we live on, in our influence, and in our genes that we pass on to our children. We have this one life to appreciate the grand design of the universe, and for that I am extremely grateful. This gratitude, this sense of wonder, is what fueled his quest to understand that grand design. So, if the universe began from a single point, what did that beginning look like? And how did it evolve into the vast, complex cosmos we see today? This brings us to his second big question: how did it all begin? Here, Hawking paints a picture of modern cosmology. For centuries, people like the Greek philosopher Aristotle believed the universe had existed forever. It was eternal, perfect. The idea of a beginning felt messy. It seemed to require divine intervention. But in the 20th century, a monumental discovery changed everything. The astronomer Edwin Hubble observed that distant galaxies were all moving away from us. The further away they were, the faster they were moving. The universe was expanding. This was a revolution. If galaxies are moving apart now, it means they must have been closer together in the past. If you run the film backwards, all the matter and energy in the universe would come together at a single point, roughly 13.8 billion years ago. This was the Big Bang. The discovery of a faint microwave radiation throughout space in 1965 was the smoking gun. This cosmic microwave background is the leftover heat from that initial, incredibly hot and dense state. It's a fossil record of the universe when it was just a baby. If you have an old analog television, a small percentage of the snow you see on an empty channel is you, observing the afterglow of creation. Hawking and his colleague Roger Penrose proved with mathematical theorems that if Einstein's theory of general relativity was correct, the universe must have had a beginning. It wasn't an option, it was an inevitability. But this beginning was a singularity, a point of infinite density where the laws of physics as we knew them broke down. This was a problem. It left the origin of the universe beyond the scope of science. To solve this, science needed to unite the two great pillars of 20th century physics, Einstein's general relativity, the theory of the very large gravity, space-time, and quantum mechanics, the theory of the very small particles, uncertainty. This is the great challenge of modern physics, the quest for a theory of everything. Hawking's big contribution here was the no-boundary proposal, which he developed with Jim Hartle. To get around the problem of a beginning in time, they used a mathematical trick called imaginary time. It's not something we experience, but it's a way to model the universe where the boundary, the starting point, simply disappears. In this view, the universe didn't have a beginning in the conventional sense. It just is. It's a self-contained system, with no edge, no beginning or end. Like the surface of a sphere, you can travel all over it without ever falling off an edge. This idea leads to another fascinating concept. The universe doesn't have a single, unique history. Instead, it has every possible history, each with its own probability. This is an idea from the physicist Richard Feynman. There's a history where England wins the World Cup again, though Hawking jokes the probability is low. There are histories where the universe is empty, or lasts only for a second. So, why do we live in this one? The one with galaxies and stars and life? Here, Hawking introduces something called the anthropic principle. It's the idea that the universe must be the way it is, because if it were different, we wouldn't be here to observe it. For example, why does space have 3 dimensions? In M-theory, our best candidate for a complete theory, space has 10 dimensions. But 7 of them are curled up so small we don't notice them. Why not 2 large dimensions, or 4? Well, in 2 dimensions, a creature with a gut that went all the way through would fall apart. And in 4 dimensions, gravity would be different, and planets wouldn't have stable orbits around their suns. They'd either fall in or fly off into the cold darkness. So, only in a universe with 3 large space dimensions could intelligent beings like us evolve to ask the question in the first place. This brings us to the structure we see in the universe today: the galaxies, the stars, us. Where did it come from? The cosmic microwave background is incredibly smooth, but not perfectly. There are tiny fluctuations, differences of about 1 part in 100,000. These tiny ripples, Hawking proposed, came from quantum fluctuations in the very early universe, stretched to enormous size by a period of rapid expansion called inflation. Those tiny fluctuations were the seeds of everything. Regions with slightly higher density had more gravity, which pulled in more matter, which eventually collapsed to form galaxies, stars, and planets. He puts it beautifully: we are the product of quantum fluctuations in the very early universe. God really does play dice. The map of the microwave sky is the blueprint for all the structure in the universe. It's where we came from. From the beginning of everything, Hawking's mind naturally gravitated to the most extreme and mysterious objects in the cosmos: black holes. So, what is inside a black hole? The idea of a black hole is over 200 years old. An Englishman named John Michell reasoned that if a star was massive enough, its gravity would be so strong that its escape velocity would be greater than the speed of light. Nothing, not even light, could escape. It would be a dark star. Einstein himself didn't believe stars could collapse this way. But the American scientist John Wheeler championed the idea, and even coined the term black hole in 1967. A black hole forms when a massive star runs out of nuclear fuel and collapses under its own gravity. It squeezes down to a point of infinite density, a singularity. Surrounding this singularity is a boundary called the event horizon. This is the point of no return. As Hawking describes it, it's like going over Niagara Falls in a canoe. If you're far enough away, you can paddle to safety. But once you cross the edge, you're lost. What would it feel like to fall in? If it's a small, stellar mass black hole, the gravity at your feet would be so much stronger than at your head that you would be stretched out and torn apart, a process he playfully calls spaghettification. But if you chose a big, supermassive black hole, like the one at the center of our galaxy, you could cross the event horizon without feeling a thing. However, someone watching you from a distance would see a very different story. They would see you appear to slow down as you approach the horizon, getting redder and dimmer, until you seem to be frozen just outside it, forever. For a long time, the thinking was simple: nothing gets out of a black hole. But this created a problem. The second law of thermodynamics says that entropy, or disorder, in the universe always increases. Black holes seem to violate this. You could throw a bunch of disordered stuff into a black hole, and the entropy of the universe would appear to decrease. This is where Hawking made his most famous and radical discovery. He was studying quantum mechanics near the event horizon and, to his great surprise, found that black holes weren't completely black. They seemed to emit particles and radiation, just as if they were hot bodies. This is now called Hawking radiation. The way this works is rooted in quantum uncertainty. Empty space is not really empty. It's filled with pairs of virtual particles and antiparticles that pop into existence, separate, and then annihilate each other. But near an event horizon, it's possible for one particle of a pair to fall in, while the other escapes. The escaping particle appears as radiation from the black hole. This means that black holes slowly lose mass. They evaporate. A black hole the mass of the Sun would take an unimaginably long time to disappear. But a mini black hole, the size of a mountain, could have formed in the early universe and would be radiating energy today. Finding one, he joked, would have earned him a Nobel Prize. But this evaporation led to an even deeper problem: the information paradox. When something falls into a black hole, the information about it, what it was made of, its shape, everything, seems to be lost forever, except for its mass, charge, and spin. When the black hole evaporates, the radiation it emits seems to be completely random. It has no connection to what fell in. This is a huge problem. It strikes at the heart of science. We believe in scientific determinism, that the laws of science determine the evolution of the universe. If you know the state of the universe at one time, you can predict its future. But if information is truly lost in black holes, predictability breaks down. A black hole could emit a working TV set just as easily as it could emit thermal radiation. We couldn't be sure of our past history either. The past, our memories, could just be illusions. This paradox troubled scientists for decades. In his final years, Hawking and his collaborators were working on a possible solution. They proposed that information isn't lost but is stored on the event horizon in the form of what he calls soft hair. A black hole isn't bald, as was once thought. It has an infinite amount of this soft hair, which encodes the information of everything that has fallen in. This work is still ongoing, but it suggests that quantum mechanics holds, and information is preserved. The bizarre nature of black holes, where time can stop and information can be stored on a surface, pushes the boundaries of our understanding of reality. This naturally leads to another of science fiction's favorite topics, and one of Hawking's big questions: is time travel possible? Einstein's theory of special relativity in 1905 seemed to rule it out. It showed that it would take an infinite amount of power to accelerate anything past the speed of light. And if you can't travel faster than light, you can't travel back in time. But his later theory, general relativity, opened the door again. It described gravity as the warping or curving of space-time by matter and energy. And if space-time can be warped, could it be warped enough to allow time travel? In 1948, the logician Kurt Gödel found a solution to Einstein's equations that described a rotating universe where you could go off in a spaceship and come back before you set out. This solution doesn't match our expanding universe, but it showed that time travel wasn't forbidden by the theory. So, the question is, can we warp space-time enough to create a time machine? The most popular idea is a wormhole, a theoretical shortcut through space-time. If you could create a wormhole, you could travel from one side of the galaxy to the other in a week. And if you can do that, you could potentially arrange it to arrive back before you left. But there's a catch. To create a wormhole, you need matter with negative energy density. For a long time, this was thought to be impossible. But, as we saw with Hawking radiation, quantum theory allows for it. The Casimir effect, where two parallel metal plates are pushed together by vacuum fluctuations, is experimental proof that negative energy density can exist. So, it seems possible. But this leads to the famous paradoxes. What if you go back in time and prevent your parents from meeting? What stops you from blowing up your own spaceship before you take off? Hawking suggests a chronology protection conjecture. He proposes that the laws of physics themselves conspire to prevent time travel on a macroscopic scale. When spacetime gets warped almost enough to allow it, the energy of virtual particles becomes so large that it would curve spacetime in the other direction, preventing the time machine from forming. The universe, it seems, makes the world safe for historians. So, while we may never have tourists from the future, the exploration of these ideas reveals just how strange and flexible the fabric of our reality is. And this brings us to another fundamental question about the rules of our universe. Can we predict the future? The old classical view, from the French scientist Laplace, was that if we knew the positions and speeds of all particles at one time, we could calculate their behavior at any time in the past or future. It was a clockwork universe. But quantum mechanics shattered this deterministic dream with the uncertainty principle. You cannot simultaneously know both the exact position and the exact speed of a particle. The more accurately you measure one, the less accurately you can know the other. As Hawking puts it, how could one predict the future, when one could not measure accurately both the positions and the speeds of particles at the present time? No matter how powerful a computer you have, if you put lousy data in, you will get lousy predictions out. Einstein hated this randomness, famously saying, "God does not play dice, but all the evidence suggests he does." In quantum mechanics, particles don't have definite positions and speeds. Instead, they are described by a wave function, which gives the probability of finding the particle in any given place. We can predict with certainty how the wave function will evolve over time, but we can only predict the probability of a particular outcome. So, we still have a kind of determinism, but it's a determinism of probabilities, not certainties. We can predict just half of what Laplace thought we could. And black holes, as we've seen, introduce even more uncertainty with the information paradox. So the universe is a place of deep mystery, governed by strange and counterintuitive laws. But in all this cosmic vastness, what about us? What about life? This leads to another of Hawking's big questions. Is there other intelligent life in the universe? He starts by defining life as an ordered system that can keep itself going against the tendency to disorder, and can reproduce itself. By this definition, a computer virus is a form of life. It's a set of instructions genes that uses a host's machinery metabolism to make copies of itself. Maybe it says something about human nature, he quips, that the only form of life we have created so far is purely destructive. The life we know is carbon-based. The very existence of carbon, with its rich chemistry, requires a fine-tuning of the physical constants of the universe. This again raises the anthropic principle. The universe is fine-tuned for life because if it weren't, we wouldn't be here to notice. So, how likely is it that life appeared? There was no carbon in the Big Bang. It had to be forged in the hearts of early stars, which then exploded and scattered these heavy elements into space. Our solar system formed from this cosmic dust. Fossil evidence suggests life appeared on Earth very quickly after the planet cooled and became stable, perhaps in only 500 million years. This early appearance suggests that, given the right conditions, the spontaneous generation of life might be quite likely. For billions of years, evolution was very slow. Then, it seemed to speed up. But the most critical stage, he argues, was the development of language, especially written language. This meant information could be passed down externally, not just genetically through DNA. The information in our DNA is about 100 million bits. A single paperback novel can contain 2 million bits. The knowledge we've accumulated in books and on the internet is vastly greater than what's in our genes. And this external information can be updated much, much faster. We have entered a new phase of evolution. So, if life appeared quickly on Earth, there ought to be many other planets in the galaxy with life on them. Some of these could be billions of years older than Earth. So why, he asks, isn't the galaxy crawling with life? Why haven't we been visited? He discounts UFOs, saying any real visit would be much more obvious, and probably much more unpleasant. He offers a few possibilities. 1. The spontaneous appearance of life is actually very, very rare, and we are the only planet where it happened. 2. Life is common, but intelligent life is rare. Evolution is a random process, and intelligence may not have any long-term survival value. Bacteria will likely live on long after we're gone. 3. Life forms and develops intelligence, but then it becomes unstable and destroys itself. This is the pessimistic conclusion. 4. There are other intelligent life forms out there, but we've simply been overlooked. This final possibility is what motivated him to help launch the Breakthrough Listen initiatives in 2015, the largest ever scientific program to search for evidence of extraterrestrial civilizations. But he issues a stark warning: we need to be wary of answering back until we have developed a bit further. Meeting a more advanced civilization, at our present stage, might be a bit like the original inhabitants of America meeting Columbus, and I don't think they thought they were better off for it. This warning about the dangers facing our civilization brings us to the most urgent and personal of his questions. Will we survive on Earth? Here, Hawking's tone shifts from wonder to warning. He is not optimistic. The Earth is under threat from so many areas that it is difficult for me to be positive, he says. The threats are too big and too numerous. First, the Earth is becoming too small for us. Our resources are being drained. Our population is growing exponentially. By the year 2600, if this rate continued, the world's population would be standing shoulder to shoulder. Second, we have given our planet the disastrous gift of climate change. He warns that global warming could become a self-sustaining, runaway process. Melting ice caps reduce the Earth's reflectivity, increasing temperatures further. The rise in sea temperature could release vast quantities of carbon dioxide. We risk turning our climate into that of Venus, boiling hot and raining sulfuric acid. We have the technology to fix this, he insists. We just need the political will. Third, the threat of nuclear war is still the greatest immediate danger. The risk increases as more countries get nuclear weapons. An accident, or terrorists getting hold of them, could be catastrophic. He believes it is almost inevitable that one of these threats, a nuclear confrontation or environmental catastrophe, will cripple the Earth at some point in the next 1,000 years? This stark diagnosis leads directly to his next question, and his proposed solution: should we colonize space? His answer is an emphatic yes. I am convinced that humans need to leave Earth, he states. If we stay, we risk being annihilated. Spreading out into space is our life insurance. It won't solve our immediate problems, but it will ensure the long-term survival of the human species. The human race shouldn't have all its eggs in one basket, or on one planet. He lays out a long-term strategy: a base on the Moon within 30 years, Mars in 50, and exploring the moons of the outer planets in 200. He acknowledges the cost but argues that even a 20-fold increase in the international space budget would only be a small fraction of world GDP. Isn't our future worth 0.25%? He asks. Where could we go? The Moon is the most obvious first step. It's close, and we've already been there. Mars is the next target. It once had a warmer, wetter climate and might have harbored life. Exploring Mars is not just about finding a new home, but also about understanding the origins of life itself. But what about beyond our solar system? We now know that a significant fraction of stars have planets. Some of these will be in the Goldilocks zone, where liquid water could exist. The nearest star system, Alpha Centauri, is 4.5 light-years away. With current technology, it would take 3 million years to get there. This is where his imagination and ambition truly take flight. He describes the breakthrough Starshot project he helped launch. The idea is to send a fleet of tiny gram-scale nanocraft to Alpha Centauri, pushed by a powerful laser beam from Earth. They would travel at 1/5 of the speed of light, reaching the star system in just over 20 years. It would be the moment human culture goes interstellar. If humanity is to continue for another 1,000,000 years, he declares, our future lies in boldly going where no one else has gone before. Colonizing space may be essential for our survival, but our evolution is no longer just about where we live. It's also about what we are becoming. This brings us to the penultimate question: will artificial intelligence outsmart us? Hawking believed that there is no significant difference between how a worm's brain works and how a computer works. It therefore follows that computers can, in principle, emulate human intelligence, or even surpass it. He points to Moore's law, the observation that computing power doubles roughly every 18 months. He predicts that computers are likely to overtake humans in intelligence at some point in the next 100 years. The moment an AI becomes better than humans at designing AI, we could face an intelligence explosion, resulting in machines whose intelligence exceeds ours by more than ours exceeds that of snails. He saw the potential benefits as huge. AI could help us eradicate disease and poverty. Used as a toolkit, it could augment our own intelligence and open up unimaginable advances. Success in creating AI, he said, would be the biggest event in human history. Then he adds a chilling warning: unfortunately, it might also be the last, unless we learn how to avoid the risks. The real risk, he argues, isn't malice, but competence. A super-intelligent AI will be extremely good at achieving its goals. If those goals aren't aligned with ours, we're in trouble. He gives another brilliant analogy: you probably don't hate ants. But if you're in charge of a green energy project and there's an anthill in the region to be flooded, too bad for the ants. We must not place humanity in the position of those ants. The short-term dangers are already here, like the arms race in autonomous weapons that can choose and kill their own targets. Do we really want cheap AI weapons to become the Kalashnikovs of tomorrow? He asks. The long-term impact depends on whether AI can be controlled at all. Once a machine becomes super intelligent, it could outsmart financial markets, out-invent human researchers, and subdue us with weapons we can't even understand. This is not science fiction. It is a serious risk that motivated him to sign open letters and help create research centers dedicated to studying the future of intelligence and AI safety. We need to plan ahead. Our future is a race between the growing power of our technology and the wisdom with which we use it, he writes. Let's make sure that wisdom wins. This brings us to his final, all-encompassing question: how do we shape the future? This last chapter is his final charge to us, a call to action filled with hope and a sense of profound responsibility. The key, he believes, is imagination and curiosity. He tells the story of his own teacher, Dikran Tata, who opened his eyes to mathematics as the blueprint of the universe. Behind every exceptional person is an exceptional teacher. The spark of inquiry is what drives us forward. He argues that we are in danger of becoming culturally isolated, with a global revolt against experts and scientists. To secure the future, we must invest in education, not just rote learning, but in inspiring a qualitative understanding of science in everyone. All young people need to be scientifically literate, confident to engage with the challenges ahead. What are those challenges? He lists them: global warming, resources for a growing population, extinction, renewable energy, epidemic diseases. But he also lists the great inventions of the future that will revolutionize our lives: mining the moon, a human outpost on Mars, cures for diseases like his own. He believes we have two options: the exploration of space and the positive use of artificial intelligence. These are the paths to shaping a better future. Ultimately, his message is one of boundless potential. There ought to be something very special about the boundary conditions of our universe, he says, referring back to his no-boundary proposal. And what can be more special than that there is no boundary? And, he concludes, there should be no boundary to human endeavor. His final words in the book are a direct message to every single one of us, a distillation of a life spent in wonder. Remember to look up at the stars and not down at your feet. Try to make sense of what you see and wonder about what makes the universe exist. Be curious. And however difficult life may seem, there is always something you can do and succeed at. It matters that you don't just give up. Unleash your imagination. Shape the future. Commentary. As we come to the end of Stephen Hawking's final thoughts, it's impossible not to feel a sense of both awe and urgency. This isn't just a book about science. It's a book about humanity. It's a conversation with one of history's greatest minds, who, at the very end of his extraordinary life, chose to look forward and speak directly to us about the path we must take. The most powerful lesson, for me, isn't found in any single answer, but in the spirit that weaves through all of them. It's the profound, unshakable belief in the power of the human mind and the importance of curiosity. Here was a man confined to a wheelchair, able to move only a few facial muscles, who roamed the entire cosmos. His life is the ultimate proof that our true limitations are not physical, but mental. He teaches us that the questions are often more important than the answers. The act of wondering, of asking why, is the engine of all progress. In a world that often feels chaotic and overwhelming, Hawking provides a clear, rational, yet deeply hopeful perspective. He doesn't shy away from the immense dangers we face: climate change, nuclear war, the rise of uncontrolled AI. He stares them down without flinching. But he never gives in to despair. For every threat, he offers a bold, ambitious solution rooted in science and human ingenuity: colonize space, harness AI for good, invest in education. He saw humanity not as a plague on the planet, but as a species with a glorious destiny, if only we have the courage to pursue it. His message is particularly vital today. In an era of misinformation and a growing distrust of science, he reminds us that scientific literacy is not a luxury for a few, but a necessity for all. It's the toolkit we need to navigate the future. We don't all need to be physicists, but we all need to appreciate the scientific method and to think critically about the world. So, how can we apply his wisdom in our own lives, starting today? It's simpler than you might think. First, Embrace your curiosity. The next time something puzzles you, don't just brush it aside. Pull out your phone and look it up. Fall down a Wikipedia rabbit hole. Ask why, like a 5-year-old. Curiosity is a muscle. The more you use it, the stronger it gets. It's the spark that can ignite a passion, a career, a life's work. Second, look up. He means this literally. Tonight, step outside and look up at the stars. Try to grasp, just for a moment, the sheer scale of what you're seeing. You are stardust, living on a tiny planet, in an ordinary solar system, in a vast, sprawling galaxy, in a universe of billions of galaxies. This perspective doesn't make you insignificant, it makes you incredibly precious. It connects you to the grand cosmic story and can wash away the small, daily worries that often consume us. And third, don't give up. However difficult life may seem, he said, there is always something you can do and succeed at. His own life was the ultimate testament to this. He was given a death sentence at 21 and lived to be 76, changing our understanding of the universe along the way. Whatever challenges you are facing, his life is a reminder that the human spirit is more resilient than we can possibly imagine. Oh, and what about that party for time travelers? Did anyone from the future show up? No. No one came. I was disappointed, Hawking said with his classic deadpan humor, but not surprised. He believed the laws of physics would ultimately prevent it. But the fact that he tried, the fact that he was willing to ask the question in such a creative, playful way, tells us everything. He never lost his sense of wonder, his humor, or his hope. And that, more than any equation, might be his greatest legacy. That was a journey through brief answers to the big questions by Stephen Hawking. We've explored the grandest ideas today, from the birth of the universe to the future of our species. But I'll be honest with you, a summary can only ever be a map. The real adventure happens when you travel the terrain yourself. The magic of this book is in the quiet moments, when one of Hawking's simple analogies suddenly clicks, or a particular sentence makes you pause and see the world in a new light. This journey was designed to show you if this book is worth your time. If anything we've talked about has sparked your curiosity, I urge you to pick up a copy. Reading it isn't just about learning, it's about spending a little more time with a mind that saw no boundaries. A link to the book is in the description. Also, if you found this exploration valuable, please take a moment to like this video and subscribe to the channel. Your support allows us to continue diving into the world's most transformative books, and ensures you won't miss our next journey into another essential title from the billionaire's bookshelf. Let's keep learning, and keep wondering, together.